Hello students, this is the latest in a series of videos based upon our textbook. This is going to cover sections 6.3, 6.4, and 6.5. Covalent bonding, intermolecular forces, and the naming, the nomenclature of covalent molecules. Non-metal atoms share some or all of their valence electrons to form covalent bonds, as we see on page 169. How exactly does this happen? Some models attempt to visualize the sharing of electrons by combining existing orbitals into new hybrid orbitals of different shapes. As an example, here you see the spherical 2s orbital, and you see the three dumbbell-shaped p orbitals at the same energy level. And in this model, they're being rearranged to form sp3 hybrid orbitals in 4 different directions. Here, the sp3 hybrid orbitals of 1 carbon and the s1 orbitals of the 4 hydrogens overlap to form the covalent bonds in a molecule of methane. Less obviously, the idea of how these hybrid orbitals connect with other atoms is sought as an explanation for the functional shapes of the actual molecules. For example, the tetrahedral structure of methane. Now, the octet rule previously taught with ionic compounds must also be obeyed by covalent compounds. For example, fluorine's in group 7A, and fluorine, as a consequence, has 7 valence electrons, as shown with the Lewis dot structure. But the octet rule says it should have 8, and so the difference between the number required by the octet rule 8 and the actual number of valence electrons is the number of electrons that would have to be added to complete the shell. In this case, 8 minus 7 is 1. And so one way fluorine could, in fact, complete the octet rule would be to add an electron. But if it does this, it's structurally balanced, but it's no longer electrically neutral. The fluorine atom has become fluoride. The solution for ionic compounds is either to gain or lose an electron in order to satisfy that octet rule, but as a consequence, they no longer have electrical neutrality. But there's another way to satisfy the octet rule in covalent molecules where you share electrons. Ideally, what you would like is to be both structurally balanced and electrically neutral. Here, each of the hydrogen atoms has 1 electron, but they also have 1 empty space. They're electrically neutral, but they are not structurally balanced. Their outer shells are not filled. But each of them has the same problem, and so they can solve that problem by sharing their electrons with each other. And so you see a Lewis dot structure that shows 2 dots in between 2 hydrogens, and that represents a pair of electrons being shared. And those pair of electrons counter the positive charges in the 2 hydrogens, but they also make each hydrogen feel as if it's completely full, electrically neutral and structurally balanced. Fluorine can do the same trick. Here, each fluorine has 7 valence electrons, which is what you expect. And each fluorine shares 1 of their valence electrons with the other fluorine. And in the process, they now have a Lewis dot structure that has the octet rule satisfied. And they are electrically neutral, but they are also structurally balanced with a completely filled outer shell. So there are different types of covalent bonding. You can have a single covalent bond. This is water. Here we see an oxygen. It has 2 lone pairs of electrons, but it's also sharing a pair of electrons with 2 hydrogens each. And so each bond between 1 hydrogen and the oxygen is a single covalent bond. Or we can have carbon dioxide. Here we see that the central carbon is sharing 2 pairs of valence electrons with each of the oxygens, CO2, and this is a double covalent bond. And you won't be surprised when I tell you that this is stronger than a single bond. It's even possible to have a triple covalent bond. Here we have carbon monoxide, and it's actually sharing 3 valence electrons. Now, this is a special case where the oxygen is actually giving up an additional pair of electrons in order to create the triple bond, and we sometimes call that a coordinate covalent bond. And as you might imagine, this bond, the triple bond, is stronger than either the double or the single bond. So covalent bonding is versatile, you might say. You can have more than one. Now, atoms pull on the electrons that they share in a bond, and some of the atoms actually pull more than others. Electronegativity is the ability of an atom of a given element to attract electrons toward itself in a chemical bond. Electronegativity has predictable trends for the main group elements in the periodic table. It increases bottom to top within a group and from left to right within a period. Electronegativities for the noble gases are not shown here as they rarely form bonds. Metals have lower electronegativities than nonmetals, and thus they have a weaker pull on electrons within bonds. So if a metal and a nonmetal try to share an electron, well, the metal is not going to be able to pull as hard as the nonmetal. Differences in electronegativity in covalent compounds can lead to bond polarity, as described in page 177 of your text. In bond polarity, well, electrons are shared in these covalent bonds, but they aren't always shared equally, which means the electrons spend more time on one side of the molecule than the other. Whether or not electrons are shared in a covalent bond depends again on the electronegativity of the atoms involved, on how greedy each element is to capture electrons. In a diatomic molecule like hydrogen, H2, both hydrogen are equally greedy. That is, since they have the same electronegativity, 2.1, their ability to pull electrons to themselves is the same. This is like a tug of war between perfectly matched teams, and the electrons in this bond spend about the same amount of time on both sides of the molecule, which is said to be nonpolar. It doesn't have a pole, it doesn't have a region that's favored in terms of positive or negative charge. Every part of the molecule has the same amount of electrons most of the time. But in a molecule like hydrogen fluoride, fluorine at 4.0 is far greedier than hydrogen at 2.1. This difference in electronegativity creates poles of partial positive and negative charge, here represented by signs delta plus and delta negative. The electrons spend more time in the region of partial negative charge. In this tug of war, the electrons spend more time on one side than the other, and so both the covalent bond and the molecule are said to be polar. That is, one side will tend to be negative, the other side will tend to be positive, like the poles of a magnet. Molecules with these polar covalent bonds adopt shapes that reflect where their electrons are most likely to be. For example, with two bonding pairs and two lone pairs of electrons around its oxygen atom, a water molecule adopts a bent shape. It is not straight, it is bent. The two polar bonds in the water molecule leads to an oxygen atom having a partial negative charge, here shown as delta minus, because it is more electronegative, because the electrons spend more time on the oxygen side of the molecule. Thus, the arrows both point toward the oxygen atom, showing the general trend. The polar bonds in this case, coming from different directions, add together, making water a polar molecule with an uneven electron density. Here we represent the difference in density in colors. The side colored red is partially negative, the side colored blue is partially positive. In the case of water, the oxygen atom has a higher electron density than the side with the two hydrogen atoms. In other cases, like carbon dioxide, CO2, the polar covalent bonds pull in opposite directions, and that tends to cancel out. The result is a polar molecule, but with a linear shape. That is, it stays in a straight line rather than being bent. Instead of having poles of opposite charge, molecules like CO2 have an electron density like a sandwich, with partially positive filling and partially negative ends. Now, small or temporary differences in the distribution of charge can lead to forces which, while individually weaker than either ionic or covalent bonds, they can be cumulatively strong. Let me say that again. You can have forces between molecules that these individual forces are very weak. They're much weaker than the actual ionic bond or covalent bond. But in a large sample of molecules, these individually weak intermolecular forces can add together, and they can be cumulatively strong and have significant effects. These forces include so-called hydrogen bonds, as well as van der Waals forces, which include London dispersion forces and dipole interactions. Now, hydrogen bonds are not actually bonds within a molecule, but they're attractive forces between a molecule and another atom. Hydrogen bonds occur when a hydrogen atom, covalently bonded to a very electronegative atom, is also weakly attracted to another electronegative atom. The classic example here shown is water. In the picture, the large red sphere labeled delta negative is, of course, the oxygen. That side's partly negative, and then each of the two smaller blue regions labeled delta plus are the two hydrogens. And so the positive side, the hydrogen side of one water molecule, tends to point toward the negative side, the oxygen side, of another water molecule. In this example, a partially positive delta plus hydrogen covalently bonded to oxygen inside one water molecule is attracted to the partially negative delta minus oxygen of another water molecule. Hydrogen bonds are the basis of adhesion and cohesion, which are two well-known properties of water. For example, water tends to adhere to surfaces, like the inside of a straw. This is adhesion. And if you look carefully in the picture, you can see that the level of water inside the straw is higher than the level of water in the glass. Why is that? Because the water tends to crawl up the inside of the straw because it's adhering to, sticking to the inner surface of the straw. And this is the basis of the phenomenon of capillary action. That's adhesion. But we also have cohesion. Water molecules don't just tend to stick to other surfaces, they tend to stick to each other. They tend to cohere with other water molecules. And this is the basis of phenomenon like raindrops and surface tension. Nonpolar molecules, like a hydrogen molecule, typically have an even distribution of charge. But from time to time, the electrons will temporarily shift. If electrons become momentarily more concentrated on one side of the molecule than the other, this causes the molecule to become a temporary dipole. That is, one side is slightly positive, delta plus, the other side is temporarily slightly negative, delta minus. This temporary dipole induces a second dipole in another nonpolar molecule nearby if it's close enough. And this in turn will cause a temporary attraction between the two molecules. Now, dipole interactions are quite a bit stronger than the dispersion forces. That's because they're not based on temporary charge differences between nonpolar molecules, but they're based upon the permanent partial positive and partial negative charges within polar molecules. As such, they tend to be stronger than dispersion forces. As an example, a polar molecule like iodine monochloride, ICl, has a partially negative delta minus chlorine side, shown in green, attracted to a partially positive delta plus iodine side, shown in purple. And they tend to pull upon their opposite number in another molecule of the same sort, in another iodine monochloride molecule. And the situation is not just that one molecule pulls on one. Each molecule can actually have multiple dipole interactions with other nearby molecules. Again, individually weak, but cumulatively strong. Surprisingly, these weak electrostatic forces provide most of the force necessary to hold molecules together in solids and liquids. These intermolecular forces exert significant cumulative effects on the bulk properties of substances, such as melting point, boiling point, and volatility. We can use volatility, a measurement of how easily a liquid evaporates, to compare the effect of these cumulative forces. Liquid bromine is held together only by the weakest of the van der Waals forces, the London dispersion force. Liquid ethanol, on the other hand, is held together with many stronger forces, including hydrogen bonding and dipole interactions. As a result, bromine is much more volatile than ethanol at the same temperature, precisely because it takes less energy to overcome the weaker forces holding it together. Finally, we come to the question of naming molecular compounds, covalent compounds, polar and nonpolar alike. The nomenclature naming rules for covalent compounds tend to be simpler than those for ionic compounds. Again, we're going to use the suffix IDE, ide, for the second nonmetal, and prefixes may be attached to one or both nonmetals to indicate the number of atoms involved. So for example, here we have the formula CO. We have a triple bond between a carbon and an oxygen. There's the first compound is carbon, and then the second, instead of oxygen, we say oxide, and we want to say how many oxygens are there, so we use the prefix mono, and so this is carbon monoxide. But with CO2, we have two oxygens, and so instead of saying monoxide, we say dioxide. Here we'll ask you to do the reverse. Instead of giving you the formula and ask you to give the name, we'll give the name and see if you can figure out the formula. A common rocket fuel has the name dinitrogen tetroxide. So you would want to go to the list of prefixes and you would discover mono, di, tri. Oh, di is a prefix meaning two, so there should be two nitrogens. And mono, di, tri, tetra. Oh, then tetra is four, so that should be four oxygens. So it should be N2O4.